Hello everyone. Today we're going to talk about the distribution of a function of a random variable. So the distribution of a function of a random variable. Let's start with an example. So suppose we have x, which has a uniform distribution from, say, -1 to 1. And we define a new random variable, say y equals x squared. And then we want to find the density of y. So that's what we're looking for. So the standard technique is to use the CDF of both as bridge. Okay, so we start with the CDF of y, which is defined as capital Y less than or equal to y. Obviously, y here has to be greater than or equal to 0 and less than 1. Zero, y equals 0 is the probability 0, so actually it doesn't really matter much. Maybe later on we have some problem because y probably is on the bottom, so we're gonna get rid of 0 later on, okay? So y equals x squared, so have that, just replacing y by x squared. And then x squared is less than or equal to y. We actually not only have we only have this piece, we also have that, so don't forget about this piece. And then we're going to integrate from negative square y to square y, the density of x. Okay, density of x is half. It's a uniform distribution from -1 to 1, and so it's a uniform distribution has a constant density, and the area has to be 1. So I, you will see in your mind, you should see a kind of a rectangle. So you have -1, 1. So it's something like this. Okay, and the area of this rectangle should be 1. That means the height has to be half. So I have half x as the uh, antiderivative. X runs from negative y, square y to square y, so I have half times 2 times square y minus plus square y. That's square y. So this is our CDF. So the density of y is the derivative. So y half times 1 over the square y. Okay. And y should be greater than 0, less than 1. Okay. So that's the basic technique. You have two CDFs. Uh, this one is not really CDF, but it is sort of, it has something to do with CDF. You can consider this capital F square root y minus of that. Yeah. So let's introduce the theory. So suppose we have a random variable x, which has a density f sub x of little x. And then we define a new random variable y, which is a function of x. And for the theory, we actually define little g to be increasing or decreasing. It's increasing or decreasing. Okay, you cannot do that like that. Okay, it has to be either decreasing or increasing. And then we further assume G is 9, so G is differentiable. Differentiable. Okay. And then we're looking for the density of Y. So the theory is like this. We start with capital F, which is the CDF of Y equals the probability of X. So what I'm talking about, Y. Capital Y less than or equal to little y. Capital Y is a random variable, little y is a scalar. And then I plug in g of x because y equals g of x. I wanted to single out x, so I use inverse function. Well, it's increasing, decreasing. Uh, let's say, assuming g is increasing, okay? When g is decreasing, I'm gonna use a different color. It's very similar, but there's some little thing which is different. So x is less than or equal to g inverse of y. If you have an increasing function, then inverse is also, I mean, you take inverse on both sides, you keep the inequality, the direction of inequality. So that equals the integral from negative infinity to g inverse of y, and you put this density of x here and dx. Okay. Now, without knowing fx, you really cannot continue. But when we are looking for the density of y, we know this is the derivative of the CDF. Okay, that means that's the dy of this integral from negative infinity to g inverse of y, and then f sub x of little x dx. All right, here we're going to use the fundamental theorem of calculus. You have an integral, you have a derivative, and then cancels out in some way. So you put this thing in here, but then you need to use the chain rule. Okay, so after we use the fundamental theorem of calculus and then the chain rule, the derivative of the integral becomes fx, okay, of g inverse of y, then times the derivative of this inverse function. Okay, so that's actually the formula. Now, when the function g is decreasing, if g is decreasing, and then you take g inverse on both sides, you actually have to change the direction of the inequality. And I'll give an example. When g is increasing, for example, x to the third. Okay, so you have a x to the third less than equal to some number a, and then you the entire sorry not the inverse function of x to the third is as x cubed. So you take a cube on both sides, you would get a to the 1/3. That's exactly this thing here. But now if you have a g which is decreasing, so it's like 1 over x. 1 over x is decreasing, right? So if you have a x 1 over x less than equal to 3, so let's assume x is positive. Okay, x is positive, but 1 over x is decreasing. And if you take 1 over you take reciprocal on both sides, you would actually get x greater than or equal to 3. Okay, because 1 over x is decreasing and the inverse its inverse is still 1 over that. You take 1 over, you take reciprocal on both sides, you would get that actually. Sorry, it's 1 over 3, not 3. So that's what this thing means. Anyway, let's continue with a blue color. So now instead of having from negative infinity to g inverse y, we would have, gee, I need some space, from g inverse of y to positive infinity, and then you have f of x. That's what we should have. But then when you can actually flip the lower limit and upper limit, you would get you have a positive here and you have a negative sign in front of it. Okay. So let's see. What should I do? Maybe I'll continue somewhere here. So you have a negative and a positive infinity to g inverse of y and then f x dx. And then you differentiate it. You would get differentiate it. There's a negative sign, okay? Similarly, I have negative and you plug in g inverse of y and then the derivative g inverse of y. So that's no problem. We have a negative sign here. It's a little bit scary, but notice that g inverse of y is actually decreasing. So the derivative is negative. Negative, negative cancels out. Actually is greater than or equal to 0. So no problem. It's good. But you have a negative sign here. You don't have a negative sign here. So to put them together, we have this formula. So f of y of little y equals fx g inverse of y. Put f's value here. So now everything would be non-negative. Okay. So that's the formula. When the function is g is increasing then or decreasing, then you can use this. So let's have a look at an example. Say x is an exponential distribution with lambda 2. Okay, so the density would be 2 times e to the negative 2x, x greater than 0. Let's define y to be log of x, and let's look at the density of y. All right, so log x is increasing, so we can use this formula, okay? And inverse function, log inverse, g of little x is log of x. That's how that's this, and we introduce this function, right? So g inverse of y, that would be e to the y. Okay, the inverse function is log, the inverse of log is e, is exponential function. So the derivative of this inverse function is just e to the y. So fy of little y, fx, which is e 2 times e to the negative, but you actually need to plug in g inverse y. G inverse y is e to the y. So you have e to the negative e to the y. And then you multiply by the derivative, which is e to the y. So we have that. Or you can put them together 2 times e to the y minus e to the y. All right. So we can still work with the density CDF. So you can also do that. Capital F of y that equals the probability of capital Y less than or equal to little y. That is capital Y is what? Log of x less than or equal to y. Log is increasing. So you have x less than or equal to e to the y. And we know exponential distribution, it's from 0 to e to the y, and 2 times e to the negative 2y. Actually, let's put x here. It's the density of x dx. And we are able to work it out, the antiderivative of negative e to the negative 2x. And then x runs from 0 to e to the y. That's 1 minus e to the negative 2 times e to the y. All right. Let me see. Did I get anything somewhere here is wrong? Uh, 2 times e to the negative lambda at negative 2x. I think I forgot there's a negative 2 here. When I plug in, there's a 2 here. The density is 2 times e to the negative 2x. And you plug in e to the y to x, you get that. So I actually have 2 here. All right. And then you differentiate it, f of capital Y, f sub capital Y of little y. That's negative e to the negative 2 times e to the y, and then the chain rule times negative 2 times e to the y. So that's 2 negative negative cancels out, e to the negative 2 times e to the y times e to the y. Okay. So they're the same. Now, if G is increasing or decreasing, then you can use the formula, but sometimes you cannot. Like what we had earlier when we deal with x squared, and the domain of x is from -1 to 1. So the function x squared looks like that from -1 to 1. Um, this function g of x equals x squared is not increasing or decreasing. So generally speaking, you should not use that theorem. Instead, you need to go through something like this. Okay. Um, when the sometimes if the uniform distribution is on an asymmetric interval, then the problem gets more complicated. Uh, I'll probably just mention it, but I'm not sure I wanted to solve it here. So, for example, I have a x which is uniform from, say, -1 to 2, and y equals x squared, and we're looking for the density of y. It's not increasing nor decreasing, so we actually need to go through the CDF. So Fy, probably y less than equal to little y, and then replace this y by x squared. This one we need to be very careful. And when y is less than 1, then it is simply the probability of x greater than equal to the square root of y less than equal to square root of y. Okay. Y is not negative. We do assume that it's greater than equal to 0. But when y is greater than equal to 1 less than 4, then we need to do this x less than equal to square root of y, but then you have greater than equal to negative, sorry, here's negative sign here, there's negative sign. All right. It's not less negative square root of y anymore because when y is greater than 1, it's negative square root of y is less than negative 1, which is out of this domain already. So you need to actually separate two pieces and then you differentiate them accordingly. Okay, so the following part should be okay because x is uniform, and I think it's you can solve it. So anyway, it will be piecewise defined function. Okay, I think that's about it. I'll see you the next time. Bye bye.